Hi, I'm Tom Johns, and I'm the MajorTim.space Honorary Young Ambassador. Today I will be speaking with Dr. Jamie Gallagher about the periodic table. Jamie, would you like to introduce yourself?
Yeah, hi Tom. So I'm Jamie, and I'm a scientist and science communicator. And my background is in chemistry and physics and engineering. So I'm an interdisciplinary scientist. And the work that I did was looking at lots of different elements and different materials and how they behave, and particularly how they behave when we combine them and we mix them. And as a science communicator, what I do is I tell people about that. I go around and I try and make science memorable and interesting. And I love to talk and share science stories.
So, we all know about the periodic table that Dmitri Mendeleev developed, but did somebody else come up with the idea before him?
Yes, actually. So we're familiar with that periodic table that Dmitry Mendeleev came up with. A few other people had attempted similar things before. But there was one big difference. Dmitry Mendeleev, the way he'd laid things out, he left gaps in his table, and that's why it was particularly important. Different chemists had tried to arrange the elements by their weight before, or from other kind of trends that they saw emerging. And Dmitry followed some of those trends that had started in the first place, but he left gaps where he felt new elements were still to be discovered. And that's something that other people hadn't really done. People tend to think, well, here are the elements we've got, let's put them into a set order. But Dmitry realized that some of them were missing. So he'd put some into order, he'd leave a little gap, and then put the rest into order. And that meant that as we're discovering new elements, we're able to slot them in. So, yes, there were several other people had designed periodic tables, and there are still people designing alternate periodic tables. But Dmitry had done something quite special.
So, how is the table that we know today different from the original one?
Well, for the first thing, its size. It's much bigger than the original table. So it was over 150 years ago that Dmitry Mendeleev put the periodic table together, and it looked very different. For a start, he wrote the columns out in slightly different ways, and so we've redesigned it to look a little bit different. But also, the main difference that he would notice if he looked at the table today is that we've doubled the number of elements that are on it. So when he was creating his table, he was sorting out just about 60 elements, whereas nowadays we have 118. So the table has been expanded, reformatted, and redesigned. He'd also find that the table is much more precise than it was in his day. Now we can measure the weight or the mass of atoms very precisely, and so it's a very accurate table compared to his rough one that was sketched out 150 years ago.
So, can you explain how the table is arranged?
Yes, there's a lot going on in there. So when you look at the table, it is a rather unusual shape. It's not the kind of standard rectangle or a square, and that's because there's a few different things are happening. The most important thing that we're doing in the table, first of all, is we're putting them by atomic number. And so atomic number is the number of protons that an element has in its nucleus. So the center of that element, how many protons, positively charged particles, are in the center. And so we put them all in order. So we have hydrogen, which has one proton, and that's element number one. We have helium, which has two protons, and that is element number two. So that's the first thing. We write them out in a big list. We then look for the trends that are appearing, and the trends are based on the electrons. So that's on the outside of the atom. And so what we start doing is we take our big list of 118 different elements and we start saying, okay, so here is one, and here's one that behaves like it. And if it behaves like it, then we're going to put it underneath. And so this gives us some lists, but also gives us some columns. And the columns are telling us how things behave. Again, that's related to the number of electrons on the outside. So the two main things that we're looking at are the numbers from the protons inside and the behaviors from the electrons outside. And so when you look at the table, if you look at where something is, you know how many protons it has inside, you know how many electrons it has on the outside, and you know how it behaves. And that's why we get a rather unusual shape.
What are the elements grouped into?
That is, so the groups that they're in, and that is a vertical column, is the electron configuration. So that is telling us how many electrons they have in their outer ring. And that tells us how they'll behave. So something like hydrogen, which has one electron orbiting around the outside of it, is very reactive. It wants to lose that electron. It wants to give it away. So over on the left-hand side, as you go down a group, all of the elements there have just one electron on their outer electron ring, and they want to give it away. Because they want to give that electron away, they are very, very, very reactive. So that's in column 1. Group 1 is one electron on the outside, very reactive. Over on the other side, at the right-hand end, all of those electron shells have been filled. They are full and they are unreactive. So that's the noble gases over at the right-hand side. So the groups are telling us about the electrons that are going to react. And so that's why it tells us how reactive or how unreactive the element is. So a group related to the electrons.
Are there any irregularities in there?
There's a few little odd quirks. We tend to think of the elements as getting heavier as we go higher. So that element number 2 is heavier than element number 1, and element number 3 is heavier than element number 4. But there's a couple, I can't remember what they are. There's a couple where that works back to front. It's not because they have different numbers of protons, it's because they have different numbers of neutrons. So inside inside the atom, you have 3 different subatomic particles that we can think about. We've got electrons, we've got protons, and there's also neutrons. So some of the elements on the table have a lot of neutrons in the inside of their element, and that makes them heavier. So the order doesn't necessarily tell us exactly the weight. So if one is before the other, doesn't necessarily mean it's lighter.
Why are noble gases called noble?
That is because of the person who discovered them. I think that I don't know. Why are they called noble gases? Let me think. Noble gases. I'm going to look it up because this is that. There's so much about the table. I forget everything. History. Noble gases. German. Okay, so it is to do with their low reactivity. It comes from German, apparently. Noble gas is translated from the German now, Elder gas, which first used in 1898 to indicate their extremely low activity. So there we go. It's from German, and it tells you they have low activity. I didn't know that. That's a new one for me.
So, which is the heaviest element in the table?
Oh, the heaviest element. I don't know. Let's look that one up as well. Heaviest element. This is why I always have this little book next to me, the Field Guide to the Elements. I should know that one. So there we go. Heaviest stable element is uranium, of course. So when we're thinking heaviest element, we could be thinking about the heaviest an atom could possibly be, or we could be thinking about the heaviest stable element. So uranium is the heaviest stable element, and that means it's like got the biggest core to its inside. We can make nuclei, the center of the element, a little bit bigger, but it's going to be very unstable. So right down at the bottom of the table, we've got elements that are lasting for fractions of seconds, like not even a full second. So heaviest stable one, uranium. Heaviest unstable one, I would guess at maybe Ognesian. Let's see, heaviest unstable element. Let's see if that brings something up. No, I can't see anything popping up immediately. But super heavy element, 117, this article saying. Why not 118? Is it one that doesn't obey the rule? All existing for confirmed. So it looks like, going by that first little Google there, heaviest stable one, uranium. Heaviest unstable one, right down at the bottom of the table, it's saying 117, which is tennessine, one of the newer ones. So basically anything down at the bottom of the table is probably going to be heavier than uranium, but it's not going to last. And so it'll break itself apart. It's almost too big to survive and it will explode. So it's kind of, there's two heaviest elements, stable and unstable.
I've asked you which is the heaviest, so now which is the lightest element?
That's nice and easy. That's hydrogen. One electron and one proton up at the very top left-hand corner of the periodic table. It really just exists as a proton, so you are not going to get anything lighter than that. And it's, if you have lots of it, then you'll notice it's light because it's a gas. It's a colorless light gas. And that is a nice, easy question.
So, next. Which is the most conductive of all the elements?
Most conductive is gold. So gold has a very, very high thermal and electrical conductivity. And that's why it's used in lots of electronic applications. So inside your phone, you would find that there are lots of gold, little junctions and things, because it has a very good conductor. Let me just see. That's right. Conductor. Best conductor of electricity. Just checking those other ones. Copper, very good as well. So best. Yeah. So silver, copper, aluminium, and gold are popping up as good ones. The reason why we might use copper instead of gold is because it's cheaper. Gold obviously is very expensive. It's also why we need to be recycling our electrical devices as well. So if this is going to be filled with gold because it's a good conductor, then we don't want to just put it in a bin. Then we want to break it apart if we're getting a new phone and take all of that gold and all of that copper and all of that silver back out so that we can reuse it. So gold, an excellent conductor of heat and electricity.
So, which was the first element that was artificially made?
First, well, let's look at a periodic table and see. So it's oh, I know what one would be the first one that would be artificially made. Let me look at a periodic table. Again, it seems like I maybe don't know much about it, and that's because there's 118 different elements. I'm going to say, I could be wrong, I'm going to look up my book. I think it will be technetium. I think, because technetium was not discovered for a very long time. It sits right in the middle of the periodic table, but it's very, very unstable. And so it was not discovered until it was created, I believe. Just trying to see. Let's see if I'm right. Let's see if that guess is right. So I'm going to say technetium. First synthesized element. Synthesized element was, yes, it was element number 43, which is indeed technetium. Yes, Ray. There we
How
go.
do
So in the early period,
scientists
very unstable, and it had to be created to be found. We knew it should exist. We knew that something with 43 protons should exist, but we couldn't find it, so it had to be created. Technetium.
So, how do scientists invent or discover new elements?
Well, it's changed over the years. So if you were living before historical records, so let's say you were an ancient Roman or an ancient Egyptian, how might you discover a new element? You might just find it. You might find a gold nugget, and somewhere in the world, you would have been the first person ever to find a gold nugget, and you just discovered that. And we don't know who did it. It's been around for such a long time, we don't know who discovered it. So that's kind of step one. Some elements we just found. Then, as we got a little bit better, then we started thinking carefully about the world around us and what it was made up of, and started looking for elements. And if you were a scientist in the 1700s or the 1800s, you might be looking for how things behaved. So, do things fizz when you put them together? Do they smell different if you burn them or react them? And so, you're looking for things that maybe do react or don't react or behave in very unusual ways. As we move forward into 1900s, something quite dramatic happened. In 1900, the first battery was developed, 1901. And that was really important for the discovery of elements because we could melt materials down and we could apply an electric current to them. And in a lot of salts, if we apply an electric current to them and you melt them down, you will separate them out into their elements. And that was happening in London in the 1900s. They were applying electric currents to lots of different melted salts and separating them out into individual elements. So that's you find them if you come from prehistory. You test things if you are the 1700s, 1900s. You're applying electric current to different things, and then nowadays we force them to exist. We bombard elements and we insert more protons, more neutrons, and force atoms together with fusion. So nowadays we create them. So it has changed throughout time from finding them to forcing them to exist.
So, what are scientists currently working on now finding the next element?
They're just trying to create it. They are just trying to think, okay, can we force this to exist? If we can force it to exist, can we see it? So that's the two big challenges with creating new elements. It's not just that you need to do something very difficult, and that is force an element to exist. We also need to be able to see that. So if it's only going to stay stable before it explodes for a fraction of a second, how do you detect that? How do you prove that it existed? So what scientists are doing just now is taking those heavy elements, trying to squeeze in an extra proton and be able to observe it before it tears itself apart. And we'll carry on doing that for a long time.
So, which was the first element to be named after a person?
The first element to be named after a person, that's something I need to look up as well. But what I can tell you is there's different trends in the periodic table. So first element named after a person. Let's have a look. Apparently, it was number 99, Einsteinium. After Einstein. But what I think is interesting is there's different trends. So first of all, you discover an element. What do you call it? Well, you look at it and you think, what does it look like? And so bismuth had a white color to it. It was associated with white. So it was called bismuth because that relates to the German word for white. So a lot of the oldest discovered elements are named after what they look like. Then we decided to change it up a little bit. We don't like naming things after what they look like. We're going to name them after something else. So let's name them after gods. So you get Mercury, named after Mercury, the Greek or Roman god. And That stuck around for a little while, so we named a few of them then. Then, as we move forward, we start thinking, okay, let's not name them after gods anymore. Let's name them after people. So we'll do things like Einsteinium and Minterium and Curium and Rutherfordium. But then that kind of fell out of use as well, and we started naming them after places as well. So there's elements named after Berkeley, and strontium as well is named after a place in Scotland. Nowadays, we're kind of back to naming things after people again. So the Ognesian, element 118, was added to the table named after the person who created it. So there's been different trends in terms of how they named them. First one, named after person, Einsteinium, after Einstein, but we've had a period of naming after properties, naming them after gods, naming after people, and naming after places. Fashions.
What was the significance of Mendeleev leaving gaps in his periodic table?
Well, as I was saying at the start, that was the big leap that he had done, to think that I don't know everything that is going to exist. Maybe there's something that we've not found. And so Dmitri effectively future-proofed his table. He left gaps so that future generations could find something and slot it right in where it belonged. And that was the big leap. So it future-proofed the table. It made it work in the 1850s. It made it work in the 1900s. And that's why we're still using it, because the gaps allow us to continue to add.
So, what is the rarest element on Earth?
Well, you could again describe this in two different ways, because the heavy elements down at the bottom, well, they only have ever existed as a few atoms. So element 114, 15, 16, 17, 18, there has only ever been a few atoms of them ever created. If you think about the rarest one that you might find on Earth, let's have a little look and see if we can find one that's rare. Okay, apparently astenine is very rare. Element number 5 is the rarest naturally occurring element in the Earth's crust. Okay, so it occurs as a decay product of heavier elements. So the very rarest, I would say 118, when we've only had a few elements ever existing. But if we want one that is going to create itself, and so that we're not having to make in a lab, astenine is the rarest, apparently, because it comes when other elements decay.
So, why do we need the elements that don't exist for long?
I'm not sure what we do. We sometimes need to discover things for the sake of discovering them, because we don't know what we're going to use them for. So the first reason that we might explore this is because we don't know which of the elements are going to be useful to us until they are useful to us. The example of this kind of scientific discovery is, sorry, I should add another point here, actually. So we discover them because we don't know about them. We are curious. We are scientists. We are exploring the world. If we also think about that process of discovery, so what do you learn as you try something? If you're trying to force elements together, you're learning about how the elements go together. You're learning to develop technologies to allow you to do very precise measurements. And so the process of that scientific discovery creates new technologies, new ways to understand the world. It's like the example you might have heard of before, that CERN, the particle physics place, they created an internet so that they could do their work. So why do we discover particles? Well, there's maybe not an immediate use for some of them, but the process of discovery is really important. So why do we discover elements that aren't existing for a long time? Well, we don't know what uses they might have in the future. And 2, during this process of discovery, we are learning a lot about the way the world works around us. It's almost like a happy accident that we also discover new elements. So it's a process of scientific discovery.
Which element in the periodic table has the largest atomic radius?
This is just like mastermind now. You're testing me. Largest atomic radius. Um, I don't know. I don't know. I don't know these things. Largest. I can work it out. So it gets smaller as it goes to the bottom right. So it's going to be on the left-hand side. It's going to be on the left-hand side, I think. What's my guess going to be? Going by the trends in the periodic table. Let me look at a table. Okay. I guess might be francium. Largest atomic radius. Francium? Francium? Yes, it's francium. Good old trends of the periodic table. As I said, if you know where it is, you can decide how it behaves. So the reason why it's francium, let me bring my table up here, is because so this is our table. As we move from the left-hand side to the right-hand side, things get smaller. And as we move down, things get bigger. And so that means that the biggest one is going to have to be over at this side because it gets smaller on that side. Small this side, big this side. So we're big here. And then as we go down, they get bigger. So the bottom right is francium. That's why it is the largest. Whew, glad I got that one right.
How do the elements get their names?
Well, we kind of mentioned this earlier. It depends on the fashion at the time. So initially, what did they look like? Then, what god do we like at the time? Then a little bit of people, and then some places. And now they are named after people again. The way they technically get their name, someone discovers something, they then go to a group of chemists called the IUPAC. So the International Union of Pure and Applied Chemists, and you suggest some names to them. You say, I've just discovered an element. Maybe this would be a good name for it. They then, over the next few years, investigate. They try and work out, have you discovered a new element? And they try and work out what it should be called. If they are happy that the element has been discovered and they're happy with the name, then they add it to the periodic table. So initially, there's some trends and fashions in the periodic table, but then there is one group of people who actually get to decide what it's called, the IUPAC.
So, is the periodic table indifferent as in other languages?
Well, it tries not to be. Is about the best answer I could give. So the idea is that we have an international standard for what the table should look like. Different countries have adopted it in slightly different ways. So for a long time, Russia didn't lay out the table as we did. They used a slightly different configuration. Effectively, we go kind of left to right and they go top to bottom. They just kind of flipped it around a little bit. So for a long time, they were using a different orientation of the periodic table. And there's little differences. So what's the example? Phosphorus. No, sulfur. Sulfur. Traditionally, in the UK, sulfur would be spelt with a PH. SUPHUR. But in America, they spell it with an F. Sulfur with an F. But there's a guidance. So although UK wants to spell it PH, America want to spell it with an F, this international union say, no, it needs to be an F. So you're supposed to spell it with an F. You publish a science paper using sulfur, which I've done, you have to use F because that's the international standard. So some of the countries have different quirks with maybe spelling or maybe pronunciation, aluminum and aluminium. But when it comes to publishing science, they all have to be the same rules because there are international standards.
So, which was the first element to be discovered and who discovered it?
We will never know. And that's the only answer we can give because some of the elements about 6 to 10 of them. We describe those as being known to the ancients. And that means that we have no written record of the person who first uncovered them. So, who first discovered iron? Who first discovered gold? Who first discovered carbon? We don't know. These will be ancient civilizations who would not have understood what they were working with. They wouldn't have known it was an element. We wouldn't know it was an element for hundreds, thousands of years. But the first person to pick something up as an element, a gold nugget, and realize this is different from all the other rocks around us, we'll never ever know.
Which is the latest element to be discovered and added to the periodic table?
So we had a few. We had, I think it was 15, 115, 117 and 118 were added to the table in 2015. So down at the bottom, we added in, where are they? I get the names right. We added in, doesn't have them on it, Ognesian, Tennessine, and the other one. So 2015, we added 3 more, bringing it up to what we now would have on the table. What are the names? My book is out of date. It doesn't have it. Because unless you look at a table that was published after 2015, it won't have their names on them. So those were the 3 that were added together. They were all discovered at slightly different times. But again, they go through this process of being verified and then being named and then eventually added to the table. So we add about 1 element every 2 years to the periodic table now. So about every 2 years, we're adding something. And we just added the last little batch, 3 altogether at the same time.
Do you have any good recommendations for books or resources about the periodic table?
Yeah, so the Royal Society of Chemistry have a really nice interactive periodic table, and you can go on, you can look at that online, and it shows you things about who discovered them, some of the uses, how rare or how we're using the elements. Also, this book that I've been bringing up a couple of times, I really like the periodic table, a field guide to the elements, and it just takes each element in turn and has a very short description about it and what it is, what it's used for. Other ones, there's a quite a famous book called Periodic Tales, which is stories from the periodic table. There's one, it's not element specific, but I quite like it. It's called The Disappearing Spoon. And that has quite a lot of element stories in it. That is how scientific phenomena has been used in quirky and weird ways throughout the year. Disappearing Spoon is a particular story, if we go a little bit of a tangent, particular story of a game that used to be played with an element back in Victorian times. Victorians, to play jokes on their house guests, would give them a cup of tea, and for a spoon, they would give them either a bismuth or a gallium spoon. So this would look like it was made of metal, and the person would pick it up, and as they stirred their tea, the spoon would dissolve and it would disappear as the metal melted. So this is the kind of the title of the book is called The Disappearing Spoon, and it's about all these different odd little stories of science, including the Victorian parlour game of giving someone a gallium spoon and having it dissolve in their cup of tea to see how they react. I hope they didn't drink it.
So, now I've got the elements in the room book here. And it also goes through every single element.
I like this one. I've got this as well in my bookcase. And where you can all find them as well. You can go on element treasure hunt.
Yeah. And it also shows you the periodic table in it.
Uh-huh. And how many elements is on it? What does it have? What's in the last box?
Oh, goodness, son.
Oh, it's up to date. Yeah, so that means, when was that book written?
2015 onwards.
Yes. I bet. What about your periodic table behind you? Is that up to date? I bet it's not.
It is.
It is. Wow. Wow. Double win on your periodic table. That's rare. Posters are always out of date. And you can tell they'll sometimes have 118 boxes, but instead of the last element being called OG, it'll be called UU something. So until they're given a name, they're given UUO or UUP, and that just is a holding name. It's a little symbol just saying, oh, we're going to give it a name.
On my poster it says, these are the 118 currently non and officially named elements that make up the periodic table. IUPAC 2016.
Yep, and those are the people that decide it all. So here's something you can watch out for that really annoys me. When you're watching TV, watch for periodic tables that they have in the background. And sometimes if you're watching a show that's set in the past, they'll use a periodic table that's up to date. Like, I'm a big Star Trek fan, and there's an episode of Star Trek where they travel back in time to the 1950s. And there's a periodic table on the wall, but they've used a periodic table from the 1990s. Other places, there was, same with Lost TV program Lost, that was on a few years ago. They had a flashback, so it was set in the 60s, and they had a periodic table in the classroom, and it was a modern periodic table. The number of elements they had on there hadn't been discovered. And the last one I can think of is Stranger Things. If you've heard of Stranger Things, the show on Netflix, there's a scene in the classroom and the teacher is talking, and behind them there's a massive big periodic table. Stranger Things is supposed to be set in the 1980s, but the periodic table that they use is from the early 2000s. And so scientists can spot these little mistakes as people have bought periodic table posters from the wrong era.
And before we started recording, I did try a frenetic.
Yeah.
The ball. So it's basically, you get a piece of paper, you've got 45 seconds, you've got little squares with all the elements on, you put them on the board corresponding, and then you've got to make words out of the element symbols.
Oh, that's difficult.
45 seconds.
That is really difficult.
Yeah, it is.
When I was at university, there was a group of people playing the game of trying to see if they could create their name out of the symbols in the periodic table. And someone asked if I could, but I fall down at the very first hurdle because my name begins with a J, and there's no J on the periodic table. Can you? Oh, you can. There's no TO, isn't there? No TO. So you can't either. What's the closest we could get for you?
And also, that was going to be one of my questions. Which letters wasn't going to be on the periodic table? And also, I've got a periodic table water bottle.
You have more periodic table stuff than I do. I'm very impressed. Yeah, I'm just trying to see if what is the closest we could get to your name. We'd have to pretend. We'd have to use like technetium. You'd have to be like team. We'll replace the O. But it's difficult to do.
So, a massive thanks to Jamie for this fascinating conversation about the periodic table. And thanks for being here.
No problem. Thanks for having me. And one thing to bear in mind is that the periodic table, like, there's a lot to it. There's 118 different elements, all with different masses and sizes and properties. And it really is just the ultimate science tool to be used. In the way that a mathematician will always have a calculator on their desk, a chemist will always have a periodic table in our desk, something that we can just grab and explore so that we can understand what it is we're working on, because it has a lot of information and, even better, a lot of stories to tell. So thanks for having me.
You're welcome.